Okay, so good morning everyone. Okay, let's start today's class. So don't forget to set your self attendance on the blackboard. Okay, so I think I can find many seats are uh, empty, so available. Okay, so even though we had some troubles, we learned about the transistors in the previous class, right? So as I mentioned, the transistor is the controllable switch. Okay, I mentioned that we can turn on or turn off switch. Okay, it's same to the transistor. So this is the symbol of the transistor, and then a transistor has three nodes called drain, source, and gate. And then actually the current can flow from source to drain or drain to source. And then we can control this current flow using gate. Okay, that's why transistor is called a controllable switch. And then we also learned that we can build a logic gate using these transistors. Also, there are two kinds of transistors, NMOS transistor and PMOS transistor. Also, I mentioned that we can see the bubble here, and then this is the logic design. Bubble represent inversion. Okay, so we can understand like this. So this is the control mode, and then if the G is 1, because there is no bubble here. So if the G is 1, then this transistor is turned on. Okay, the turned on means that the electric current can flow through the drain to source or source to drain. So if the G is 1, then it's turned on. And as you can see, we can see the bubble here. So it means inversion. So which means for the PMOS transistor, if the G equals 0, then the electric current can flow from source to drain or drain to source. Okay, so and then by combining with the two kinds of transistors, NMOS transistor and PMOS transistors, we can build electric circuit. Then I mentioned that we can assign PMOS transistors the full of network. The full of network means that one node of the PMOS transistor is connected to the VDD. Okay, then I also explained the reason why we assign the PMOS transistor the full of network. Because PMOS transistor is a good switch that can pass 1. Okay, it's a good switch for signal 1, but it's a poor circuit. It's a poor switch for ground. That's why we allocate PMOS transistors on the full of network. On the other hand, the NMOS transistor is a good switch for signal 0. Okay, that's why the NMOS transistor is connected to the ground. Okay, and then also the output is connected. Output is filled by PMOS transistor network and then NMOS transistor network. Okay, also I explained how to implement the basic logic gate with CMOS transistors. Okay, so this is the transistor circuit of NOT gate. Okay, and then also I explained how we can figure out the operation of this NOT gate. Okay, so this figure, the A is the input, it's a control signal. So as you can see, the A is connected to the gate of the PMOS and NMOS transistor. And then based on this A signal, we can also figure out the operation of the PMOS and NMOS transistors, right? So on and off, and then the Y input is high. If it's PMOS network, the full of network is turned on. The turned on means that these PMOS transistors are connected to the VDD, right? So if it's turned on, then Y is connected to the VDD. So the voltage level becomes high. The high voltage represents 1 in the digital circuit. So that's why 1 becomes 1. When on input is 0. And then on the other hand, if we input is 1, then its MOS transistors are turned on. So it means that output is connected to the ground. Okay? If its output Y is connected to the ground, then the voltage becomes low. Low means 0 in the digital circuit. Okay? And also we can build NAND gate like this. Okay? And then also I explained this is the 3 input NOR gate. And then also I explained how to build AND gate. So I mentioned that the MOS transistor is connected to the ground, and then also actually as you can see the MOS transistor is connected like this. Okay. So the control signal is if the control signal is 1, then it's turned on, and then 0 is turned off. So actually we can easily understand the operation of the MOS transistor. But the operation of a PMOS transistor is the inverse of the MOS transistor, right? Because we can find bubble here. So actually, we can understand the operation of the NMOS transistor in the inverse way. Okay. But the NMOS transistor is connected to the ground, which means that actually, when the NMOS transistor is turned on, then the output signal is connected to the ground. So which means that output becomes 0. So 0 means actually false in the digital circuit with the negation of digital circuit. So which means if the control signal is turned on, so if the control signal is high, true, then the MOS transistor is connected to the ground. So it generates the false output. It make output signals false. Understand? So you can understand, oh, input is 1, then because of the MOS transistor, the output becomes 0. So it's kind of not inversion. So actually, if we just combine the MOS transistors and the PMOS transistors, actually we can easily, using this MOS transistor and PMOS transistor, so we can easily build inverted logic. So actually, as I mentioned, we can build MOS inverter. So it's a NOT gate like this. Okay, and then it's a NAND gate. Okay, but it means that it's not easy to build and OR gate, like not inverted gate. Okay, because using the MOS transistor, we can easily build inverted gate, but it's not easy. So I mentioned that we can build AND gate using the NAND plus inverter. It's a NOT gate. Okay, the CMOS transistor logic. Also, I explained about the transmission gate. Transmission gate is also the switch, but I also mentioned that MOS has once poorly. That's why we use MOS transistor in the pull down network, and PMOS has zeros poorly. So by combining MOS and PMOS transistor, also you can. So this is, we can see the bar here. Okay. So bar means inversion. Okay. So actually for the PMOS transistor, the bar of enable is So this bar of enable is given to the PMOS controller, the gate of the PMOS transistor, and the enable signal is given to the NMOS transistor. But if we just see the operation of the NMOS transistor, then we can easily figure out the operation of this transmission gate, right? So if the enable is 1, then gate A is connected to B. So if enable is 0, then A is disconnected from B. Okay, easy. So if you understand the basic operation of NMOS and PMOS transistor, then actually if you see the circuits composed using the NMOS and PMOS transistor, then we can figure out the operation of this PMOS transistor circuit. Okay, we can understand like the digital operation of the PMOS transistors. Then actually one of the students asked a question about the detailed operation of the MOS transistors. Actually, it's not easy to explain the detailed operation of the MOS transistors within this one class, but it's complex actually. So, but using the digital concept, we can simplify the operation of the NMOS and PMOS transistors. Okay, so in this course, it's okay, it's enough. Okay, so if you are interested, then you can search the detailed operation of MOS transistors. Okay, actually the detailed operation of the MOS transistor is determined by some the electric physics, and then also the high level electric physics depend on the electric physics and the high level electric physics. Okay. Yeah. Okay. 그렇죠? 네, okay, yeah, this is typo. Okay, good question. Good. Yeah. So it's a good question. Yeah, it is a typo. So if EM is equal to 1 and A is connected to B. Okay, sorry about that. Okay, so now, let's discuss about the power consumption of the electric circuit. So actually, the computer processors, CPUs, are electric devices. So which means that in order to run the CPUs, then we need to connect the CPUs to the VDD. So actually, the electric powers need to be connected to the CPU. So which means that actually, if you see let's see the inverter circuit. Okay. So actually, the one node of the inverter circuit is connected to the VDD. Okay, and then another node of the inverter circuit is connected to the ground. Okay. And then based on the control input A, the output is determined. So actually, in this circuit has the capacitor here. Okay. So which means based on this input A, the electric current can flow to the capacitor. Okay, the electric charge can be poured into this capacitor, and then if based on the operation of this CMOS transistor circuit, then also if this NMOS transistor is connected to the ground, so electric charge is transferred to the ground. So I want I would say based on the operation of the input, then this circuit generates the electric current. Okay, that's what I want to say. So based on the input signal A, this circuit generates the electric current. Then what does that mean? The circuit is connected to the VDD and ground. Okay, and then the electric current I is generated by input signal. So VDD is a voltage difference, and then the current is generated between the different voltage levels. And then the circuit will consume power. Okay, so because power equals I multiplied by V. So I mentioned that in this circuit, based on the input signal A, electric currents are generated. So this power consumption is called dynamic power consumption. Okay, it is because the power consumption is decided by input signal A. So it is dynamically changed by input signal A. Also, we can observe the different kind of power consumption. So this kind of power consumption is called the static power consumption. So static power consumption means the electric current from this VDD to the ground. But you may think, oh, so if you understand so if you are very observative, then so you may think that, oh, this is the switch. So actually, so if the A is 1, then the switch is off, right? And this switch is on. So which means that this, if we just focus on this wire, then actually, if the PMOS transistor is disconnected, right? And then if the A is 0, and then actually the NMOS transistor is disconnected, so actually the circuit is not generated from this line, from VDD to the ground. So you may think that, oh, in the CMOS transistor circuit, there is no static power consumption. But not true, because so actually I simplify the operation of these MOS transistors using the digital concept. But I said that actually these circuits are operating in the real world. It's actually analog world. So which means that in the very short time, this line can be connected from VDD to the ground. The very short time. Okay, so power can be consumed statically from this line. Also, another problem is that this PMOS transistor, these transistors are not perfect switch. So what does that mean? It's not perfect. So think like the normal switch. So if we turn on the switch, that is electric devices also turn off. If we turn on the switch, then the electric device works. So which means that we can turn on the lamp or the classroom. But so and then if we turn off the switch, then this lamp is also turned off. So which means that the current does not flow to these electric devices based on the switch. But it's not true for the MOS transistors. So even though we turned off these MOS transistors, more amount of current can flow through this transistor, even though this transistor is turned off. Okay, that is the source of static power consumption. So you can just understand that because this switch is not a perfect switch. Okay, so we can understand the operation of this both transistor like the digital switch, but it's not true in the real world. It's not a perfect switch. So current can flow through the drain to source or source to drain, even though the transistor is on off. Okay, so it decides the static power consumption. So think like this, even though you turned off the sorry, it's not a good example. So in the idle operation mode, so in the idle operation mode of your smartphone just still consume power, right? So that's the example of the static power consumption, but it's not a good example actually. Okay, this is the equation that calculates the dynamic power of a circuit. Okay, actually, as I mentioned, I need to again, so it's the input, and then it's the PMOS transistor is connected to the ground, and then NMOS transistor is connected to the CMOS transistor is connected to the VDD, and the NMOS transistor is connected to the ground, and then this is the output. And then actually, there is a capacitor, the output. So the capacitor which is output is set as C. So this is the capacitor. There's a capacitance. And then also the C can be connected to the VDD and ground here. So the power consumption in this capacitor is determined as the C VDD squared. Okay. So actually, if you learn the electric circuit, then you can understand why this power consumption of the capacitor is the CVD squared. Okay, also this circuit is working. So this circuit works based on the input signal. But actually, so we will learn about the clock, the digital signal that works with the clock signal. But you can just understand this frequency F. So the F means the clock frequency of this circuit. So clock means that actually the digital circuit runs with clock signal. So for example, when you purchase a CPU, then you can check the clock frequency of the CPU, right? The clock is the periodic signal that can run the digital devices. Okay, so the clock signal. Okay, so F is the frequency of the clock signal, and then the alpha is actually the activity factor of this circuit. So dynamic power consumption is determined like this: the alpha, so it's an activity factor. So it's the activity factor of input signals, and then C VDD square is the power consumption in this capacitor, and then F means the clock frequency. Okay, so this is the dynamic power consumption of this circuit. So which means that if we turn on and then if we learn the digital circuit, then this digital circuit consumes dynamic power like this. And then this slide shows the activity factor of the various circuits. The activity factor of the clock signal is 1. So as I mentioned, the clock signal is the periodic signal that is provided to the every digital component. Okay, so actually we will learn about the clock signal in the later part of this course. And then if this data switches once per cycle, okay, and the activity factor becomes 0.5. So you don't need to understand this now because we will learn about the clock signal in the later part of this course. So this is the typical activity center of the various data. And then I also mentioned the static power consumption. So static power means that even though the input signal does not change, but the circuit can consume power, as I mentioned. So no gates are switching, but the power is consumed. So actually, static power, the equation of the static power consumption is very simple. The P equal IB, right? So it's a very simple equation of the power consumption in the circuit. So static power is determined like this. So I said that, so this is the BDD, right? And then the current can flow from this BDD to the ground when we consider the static power. So IDD is the current that can flow from the BDD to the ground. Okay, based on the some conditions, we can calculate the dynamic power and then static power of this direct system. So it's a very simple equation. Okay, it's just a simple condition, simple assumptions, and based on the simple conditions, then we can calculate the dynamic power and static power of this system like this. Okay, so if this value is given, we can just allocate these conditions, these values to the equation. Okay, so we can calculate the power consumption of this time circuit. Okay, so this is the end of the chapter 1, and then please read the chapter 1.7 and then 1.8. Okay. So I plan to post the first homework assignment to the Blackboard today or tomorrow, okay, because we complete the chapter 1. Okay, so now we are in the chapter 2, and then we will learn about the Boolean equations. Okay. Okay, let's learn about the combinational circuit. So when I explain about the CMOS circuit, then I frequently use a terminology circuit. Okay, but as you can see, the title of this part is the combinational circuit. So you can find the circuit here, like the CMOS circuit, and then also you can find the combination. Then we need to know the definition of combinational circuit. Okay. Okay. Then let's see the basic module of the digital circuit. So what can you see? You can see the rectangles. Actually, it's a box. Okay, here there's the rectangle shape, and then you can see the inputs, and then you can see the outputs. So actually, logic circuit or typical logic circuit is composed of, as you can see, input here. Okay, so there is input here. So it is, so as you can see, there can be multiple inputs to this module, what is the circuit. And then also, if the input is given to this circuit, then this circuit generates the output. Right. And then we can define the operation of this circuit, right? And then this is called the functional specification. So for example, if the Y is the output of this module or this circuit, then Y can be defined like the function of A. A is the input, right? So we can define the function of the app. So it's like the black box, and then the function is defined for this box. Very simple, right? But we are learning about the hardware, and hardware works the real world. Then we also have the timing components. So, digital hardware is defined that digital hardware has these components, the input signals, the output signals, and the functional specification, the function of this module or this circuit. Also, we need to define timing. Then what is the timing? So if you see the functional specification of this is the circuit, then we can easily define the output from the input signal. So like y equal f, the function of the a. So similar to the function of the mathematics, the algebra. But actually, in the real world, the output signal changes at some time, and then this is called the delay. Actually, delay of the circuit. Okay, delay. So actually, the input signal changes, then output signals also modified. Output signals are modified, but at a certain delay, like a t. Okay. So we also need to know the timing specification of the digital circuit. Okay. So which means that we need to know the delay of the circuit. The output is changing after some delay of input changes. Okay, because this is the hardware works in the real world. Okay. Okay. Let's see what circuits are, which means a definition of a circuit. So I also frequently use the terminology circuit. Then I believe most of you know about the circuit because we learned physics, okay? Electric physics. So then, now what is a circuit? What is a circuit? So this is the definition of a circuit from Wikipedia. So actually, the circuit is composed of a voltage source, okay, power source like the battery, and then this power source is connected to some electric components like the resistors and capacitors and inductors, something like that. And then also this wire, metal wire, is connected to another node of the electric power source. So actually, the terminology circuit comes from circle. Okay, circle. Why? If we see that this circuit, then we can find that we can find the circuit is connected to the one node of this power source, and then another this circuit is also connected to the same power source usually. Okay, this is the very simple circuit. So it's also if we see the circuit like the inverter, so you can find that so this is the inverter. Okay. So we can find that this node connected to the VDD, and then this node, is not connected to the ground. So like this one, so this is the VDD node, and this is the ground node. So which means when the digital circuit actually this is not a separate form, but the one node is connected to the VDD, and one node is connected to the ground. And also we can think that these transistors are electronic Hy is called a circuit. It's a digital circuit. So which is that electric components are connected to the power source, and then based on the electric signals, then the circuit can generate some electric outputs. So that is the definition of a circuit. Okay. Then we are learning about the digital circuit. So which means that digital circuit receive the digital inputs and then generate the digital outputs. But I mentioned that this the circuit is the electric circuit. So this the circuit generate electric output signals. Okay. Okay, let's see the some definition. So you can see this large box here. Oops. You can see the large box here, and then also you can see the smaller multiple boxes like E1, E3, and E2. So actually we can organize the circuits like this. So by combining multiple smaller digital circuits, then we also build the larger digital circuits. So this is the modularity, so also hierarchy. So let's see the definition of this module. So you can find the input signals here. So A, B, C are called inputs. So you can find the output signals here, Y and Z. But you can also find that inside of this box, then you can find some wires. Okay, so this wire. So if you see this wire is connected to the input A, and then this wire is given to the another element E1. Okay. And then if you see that this wire is called this wire is connected from elements E1 to E3. So actually, inside of this circuit, we can find many connections. Okay, so these are input signals. Input is also kind of wires or connections. So we can see the output signals. But inside of the digital circuit, then we can also find many connections, so many wires. And then this wire is called the internal node. So internal signals or internal node. So internal node. Okay. And then also, as I mentioned, by combining multiple digital circuits, then we can build larger circuits. Okay. And so these are called the elements. Also, these are also circuits. Okay. You can build a digital circuits like this. Also, these are definition of some terminologies in digital circuits. Okay. Also, there are two types of logic circuits. So the one type is the combinational circuit, and then another type of digital logic circuits is the sequential logic. So actually, the combinational logic is simple. It's easy to understand. So it's like the black box here, and then this is the input, and this is the output. Okay, and then we can define the function, the functional specification of this circuit, right? Like the F equal some inputs I1, I2, I3, like this, and then the output is determined by function of inputs. So if the output signal is determined by only current values of inputs. So output, if the output signals are determined by only input signals, then this kind of logic is called the combinational logic. Okay. So you can say that this is the memory list. Okay. Then what is the sequential logic? So you may think, oh, until now, so we learned that this the circuit looks like this. Why the output signal is determined by function of inputs? That's what we learned up to now. Then what is the sequential logic? Actually, the sequential logic is the output of the sequential logic is determined by inputs I1, I2, I3, and state. Previous states or current previous states. What does that mean? So actually, so when we organize a system, the system can be in the different states. Okay. So like so for example, in your smartphone, the smartphone works in the different working states, like the running states or idle states. Okay. So actually, based on the input, the state of this circuit is determined. That is the previous result from previous states. And then output of the circuit is determined by input signals and previous states. That is called a sequential logic. It's kind of a sequential logic. So in order to generate the output of the sequential logic, then we need to know the previous states, so states of this circuit. So which means that we need to store these states in the circuit. So sequential logic has memory. If some data is stored in the circuit or some data is stored in the system, then we can say that, oh, this system has memory. Okay, that's why sequential logic has memory, because sequential logic use as states to generate the output. Okay, so this is the internal states. But if we combinational logic is very simple. That's why we learn the combinational logic first. The output of a combinational logic is only determined by current inputs. Okay, so that's why the combinational logic is simpler than the sequential logic. Okay, so we can say that combinational logic is memoryless. So it is because we don't need to store the state of this logic. Okay, so firstly, we will learn about the combinational logic. Then we will learn about the sequential logic. Okay. Then what are combinational logics? And then this slide explains the rules of composition. So what does that mean? So this slide explains what combinational logics are. Okay. So as you can see, so what is this? We learned about the basic logic gate. So what is this gate? It's AND, right? It's this AND. And then this is OR, right? So, sorry, question. Is AND gate combinational logic? Think like this. Is AND gate combinational logic? Yes or no? Is that? AND gate is a combinational logic, right? Because the output of AND gate is only determined by inputs, right? So this is the equation of the AND gate, right? It's a multiplication. So the function, the output of the AND gate is the AND gate is determined by AB. Then how about the OR gate? OR gate is also a combinational logic, right? Because this is the Y equal A plus B, right? So as I mentioned, we can build a larger circuit using the basic gate or basic smaller combinational circuit. So if all elements are combinational, then if this logic is a combinational logic, then these elements are need to be combination. So which means that we can say that this is the combinational logic. Okay, this large box. Then we can also find smaller elements inside of this box. But if this large box is a combinational logic, then these elements must be combinational logics. Okay? If one of these logic is sequential, then is the large box is a sequential logic. So which means so all elements must be combination. And then every node is either on input or connected to exactly one output. What does that mean? So actually, if you see that this node, this line, then this line is connected to the only one input and one output. Okay, so this is internal node. The internal node is connected to one input and one output. Okay, and then the circuit contains no cyclic path. So which means if this logic has the feedback path like this, the cyclic path, then it's not a combinational. Okay. So this is the conditions for combinational logics. Then questions. Is this a combinational logic? A. Yes or no? So based on these conditions, so if this logic is a combinational logic, then this logic needs to meet these conditions, right? Then is this a combinational logic? A. Yes or no? Yes, right. So so this is a combination logic. Okay, so this is not gate. Then also this is not gate. Also, it's not only so it meets the second condition. So this is the combination logic. How about this? Is this a combination logic? No, because of the feedback path. The cyclic path is here. Okay, so this is the same figure, the combinational logic. How about this? So is this a combinational logic or not? So all elements are combinational, but if we see that this node is connected to the two inputs, right? Then connected to the one input. So actually, this is not a combinational logic. Okay? Because if we see that this node is this node is driven by two input. So this node is connected to these two inputs. So this is not a combinational logic. How about this? So in this figure, the CL represents the combinational logic. Okay. So I also frequently use the CL. CL represents a combination logic. Then how about this? Logic E. Is this a combinational logic? Yes or no? Yes, right. Because all elements are combinational, and then so the node is properly connected, and there is no feedback path, cyclic path. So this is a combinational logic. And how about this? This is not a combinational logic because this feedback path. Okay. So when we then I'll explain why this is not a combinational logic. So if you see that this logic, I mentioned that in the combinational logic, the output is only determined by inputs, right? But if you see that this logic, how about this? Actually, the output is given to the another input of this CL, the combinational logic. So it does not meet this condition, right? So that's why if the circuit has a feedback path, the cyclic path, then this circuit cannot be a combinational logic. Okay, you understand? Okay, so now let's learn about the Boolean equation. Then what is the Boolean equation? So we already know about an equation, right? So what is an equation? If some it's called also an equation. So but if we just mention an equation, then this equation just handles numbers, and then we can generate some equation with the equal sign. Okay, so actually that is the normal equation. Then what is the Boolean equation? So actually it's just simple because the Boolean equation just handles true or false. Actually, normal equations in the real world handle numbers, okay, decimal numbers or some other numbers, but Boolean equations just handle true or false, and that's it. So actually, Boolean equation is much simpler than the normal equation, right? Also, Boolean, we will also learn about the Boolean algebra. The Boolean algebra is also much simpler than the normal algebra. Okay, let's see this example. So also you can see the combinational logic here. Then we can represent this combinational logic using Boolean equation because there are two outputs. So we can represent the functional specification of this combinational logic using Boolean equations. Okay, which means so there are two outputs here. So each output has the functional specification from A, B, C in. Okay, so input signals. So we can define the functional specification of the output as. So we can define another functional specification of output C out. And then we can define this functional Boolean functional specification using Boolean equation like this. What does that mean? S equal A exclusive over B exclusive over C. Okay, so which means that we can generate output S using 3 inputs and then exclusive ORs. Exclusive ORs of 3 inputs. Okay. How about the C out? Okay, we also represent the output C out using this equation. Okay, it's similar to the normal equation, right? AB plus AC plus BC. Okay, it's a simple, right? So this multiplication represent, and because it's a Boolean equation, the Boolean equation just handle true or false, and then we also learned that the multiplication, this the logic represent AND gate. Okay, and then this plus. What is this plus sign? Is OR, right? So the C out, we can represent C out using an equation. So and then this equation is a Boolean equation. Okay, so we can represent the output is the actually simple logic gate, the Boolean equation. So if you see that this equation, actually the form of this Boolean equation is similar, actually same, very similar. It's very similar to the normal equation, but the definition is a little bit different. Also, operator like we can use the exclusive OR. So we can use the multiplication and then addition for Boolean equations, but the definition is a little bit different. Okay, that is Boolean equation, easy, right? So we can write equations. Okay, and then let's see some definitions, the Boolean equations. So these are definitions, so you need to memorize just definitions. Okay, those are definitions. So complement. So complement means a variable with a bar over it. Okay, what does that mean? This bar, it represents inversion. We already know, right? So this bar represents the inversion. So inversion means true is changed to false, then false is changed to true, right? So bar, so this is called complement. And then literal. So literal means that it's a variable or its complement. These are examples. So these are called literals. A or A bar or B or B bar. Okay. And then implicant. Implicant is a product of literals. And product represent multiplication, right? Implicant is a product of literals. So which means that in this implicant, so we can use A, B, and C bar. Okay. So by using literals, then we can generate implicant. It's the product of literals. Okay. And then mean term. So mean term represents a product that includes all input variables, the product. So what does that mean? So this is the combinational logic. You see combinational logic, and then combinational logic may have 3 inputs. Or this let us assume that this logic has 3 inputs A, B, C, and then the mean term means that is the product, so using the ABC, so all ABC, so in all input signals, but we can use the literals of all input signals. So which means that we can use all ABC to generate the product. So this is called midterm. Okay, the next term is the sum that includes all input variables. Okay, so this is the example. Okay, so if we generate what is it? So if we generate sums using a sum using all input signals, then it's the max term. Okay. So actually these are definitions, so you need to memorize. Okay. Okay. Also some definition, it's an order of operations. Like normal equation, the Boolean equation has also priorities. What does that mean? So in a normal operation, like y equal x c plus x c plus it's not good example. Sorry. So what y equal a x square plus e x plus c. So if you see that this equation, it's a normal equation, then we already know the priority of this equation. Which means we first compute the multiplication first, and then we can just compute add or subtract, addition or subtractions, right? So multiplication and the division has higher priority than the addition and subtractions, right? It's the same to the actually Boolean equation. So this is the example of a Boolean equation, y equal a plus b and b bar. Then not bar has the highest priority. So we can just set the highest priority to bar. So we just first compute the C bar. Okay. Then the next priority is set the multiplication product, which means and. Okay, it's similar to the normal equation, right? So actually, I believe we can easily understand the priority of a Boolean equation. Okay, because the product has the higher priority than the sum. Okay, and then we perform sum. Okay, sum means or. That is the priority of a Boolean equation. Okay, then let's learn about the sum of products. So what does that mean? SOP. It's called SOP. So sum of products. So products represent multiplications, right? And then sum of products. So it's similar to the y equal AB plus BC plus CD. So if you see that this equation is a products, and then is y equal sum of multiple products. So some SOP, sum of products has a form like this, sum of product, okay? By definition. Okay. All Boolean equations can be written in sum of products form. Okay, So which means that using SOP forms, you can represent all types of Boolean equations. All Boolean equations. Okay? All Boolean equations can be represented using SOP forms. So which means we can use the SOP form to represent a certain Boolean equation. So I don't know. So in order to represent a function of a certain logic, so like a certain logic here, and then this is the output of the logic, and then this logic may have multiple inputs like A, B, C, D. Then in order to represent Y, in order to represent output Y, we can combine all inputs in this logic, and we can represent the functional specification of this Y using SOP form. Okay, so which means, so this output Y can be represented using SOP form. So you can use any result can be represented using SOP form. So in order to represent this functional specification of this Y, then we can just firstly generate min term. So what is the min term? So by definition, min term represents the product of all input variables, right? So this is the example. So this example shows that this is the different circuit. And then this different circuit has the two inputs A, B, and then one output Y. And then as you can see, this is the truth table of this circuit. Okay. So we can define the min term based on the input signals A and B. Okay. So min term is the product of all input signals, right? And then in order to represent this line, and then we assume that so in order to make this Y as 1, then what is the min term of this equation? So it's just an assumption. So I actually in this example, the Y is 0, but in order to figure out min term of this line, then we assume that in order to make Y 1, then we can set the min term of this line. Okay. So in order to make this Y equal 1, then min term of this line is the A bar and B bar, right? So this is a 0 and this is a 0. So then this is the N, right? So which means that A bar is 1 and then B bar is 1. So the result of A bar and B bar is 1. So this is 1. But it's just like in order to figure out min term of this line. Okay. So min term of this line is the A bar and B bar. So we can know the figure of min term of the other lines like this. So it's got 0, 1. So which means A bar and B. So you can just think like that. So if this is 0, then it's the bar. And then 1, it's just this signal. Okay, these are min terms of for the input. And then if you see the output, then this output is 1 only for this line, then this line. Right? Then how can we define this output signal y. So in order to so in this circuit, the y is 1 for this midterm and this midterm, and then this is 1. And then we are learning about the sum of product form. Okay, so in order to make y1 only for these cases, then we just combine midterm like this. So this is a midterm of this line, right? So it makes y as 1. Okay, so we require A bar and B. And then with also another line that can make y1, this line. So we can make y as 1 using A and B. And then y is 1. Y can be 1 if A is 0 and B is 1. And for these two cases, y can become 1. So it is or. So which means if the A is A bar and B, this is the midterm of this line. And then or A and B, then y becomes 1. So I said or, right? So that's why we use add. Add means or, right? So in order to make y for this case and this case, we use midterm of this line here and here. And then we already know that if this midterm is met, then y becomes 1. Or if this midterm is met, then y becomes 1. That's why we use the product of sum of 영어랑 한국어랑 달라서 그런데 product first and then sum of product. Okay, we can generate the product first and then sum of generated product. Okay, so we can define the output of this y like this. So this is the result. So using the first table, we can define the midterm of every row, like here, and then we can select the row that can make y1. Okay, so there are two lines here, this line and this line. So we can know the midterm of this line and this line. Then we already know that y becomes 1 if this condition is met, or and then this condition is met. So we can represent the result y like this. Result y is the function of A and B, and then using the sum of product form, then this is the midterm, and this is the midterm. They can make y is 1. Then this is or. So we can represent the y as the A bar and B plus A and B. This is the equation of output y. That is represented using SOP form. So actually, if there is a SOP form, so there is POS for product of sums form. But I think I need to stop here. We will learn about the POS form in the next class. Okay. Any questions? Thank you for attention. See you in the next class. 감사합니다.